Hi there again, Gordon West, WB6NOA, and this is, if you're on cassette, your second cassette in preparation for your extra class amateur radio license. Well, what do you say we go from CW over to this mode right here called, that's right, packet radio. E2D01. Our first question says, what does CMD when you see it displayed on the video monitor of your packet station? Well, CMD is the TNC, Terminal Node Controller, indicating the command mode when to receive instructions from the keyboard that you're sitting right beside. And we are right now tuned into a packet cluster bulletin board. That is a packet bulletin board devoted primarily to serving a special interest group. And DXers love those packet clusters. That lets them know when the hot stations are out there. Now, in comparing high frequency and 2-meter packet operations, which of the following is not true? Well, what is not true is that HF packet is limited to amateur extra class licensees. No. HF packet is open to all ham licensees who have the right license to operate up on HF. Now, what is the purpose of a digital store and forward mode in an amateur satellite? Well, digital store and forward allows a store message in an amateur satellite for later download by other stations. So satellites with store and forward have a great way of sending a packet all the way around the world. And which of the following techniques is normally used by low Earth orbit orbiting digital satellites to relay messages around the world? That is store and forward. Well, let me dial around here, and here we are up on the 2-meter band, and let's go to the Automatic Position Reporting System Frequency, APRS. I'm tied into not only my terminal node controller, but I've got a little GPS tied into my radio, so I'm able to send out my location. The question is, what frequency do we tune in? There it is, 144.390 megahertz. Which of the following digital protocols does APRS use? And we use AX.25. That's the ham version of a commercial packet networking operating X.25. The AX.25 protocol is recognized and authorized by the Federal Communications Commission with specific speed limitations so that we don't exceed our bandwidth on the worldwide bands. And which of the following types of packet frames may be used to transmit APRS beacon data? This is unnumbered information frames. Unnumbered information frames. Under clear communications condition, which of these digital communications modes has the fastest data throughput? And that would be 300 baud packet. Faster than PSK31, faster than RTTY, faster than AMTOR. And how can an APRS station be used to help support a public service communications activity like a walkathon? Well, an APRS station with a GPS tied into it can automatically transmit information to show the station's position along the course route. And which of the following data sources are needed to accurately transmit your geographic location over an APRS network? Well, you'll need a GPS receiver with the NMEA 0183 formatted data. You need latitude and longitude coming out of a GPS set. And if you're using, let's say, a LORAN receiver, you'll need an NMEA 0183 formatted data. All of these choices are correct to accurately transmit your geographical location over the APRS network. Well, there's a news sound. What is the most common method of transmitting data emissions below 30 megahertz, such as on the HF band? And that would be frequency shift keying of an RF carrier below 30 megahertz. One of Ham's favorite transmission mode is called AMTOR. Stands for Amateur Teleprinting over Radio. And this is a digital mode with error correction leading to perfect copy when band conditions are favorable on worldwide frequencies. FEC stands for Forward Error Correction, AMTOR Mode B, where each character is sent twice. So what do the letters FEC mean as they relate to AMTOR? Forward Error Correction. How is forward error correction implemented? By transmitting extra data that may be used to detect and correct transmission errors. Now, if our oscilloscope is connected to our TNC, or terminal unit, and is displaying two crossed ellipses, which I'm doing on my computer right now, and then all of a sudden one suddenly disappears, what would that indicate about the observed signal? Well, this is called selective fading, and that's what happens when you lose one of those crossed ellipses. Now, what is the name for a bulletin transmission system that includes a special header to allow receiving stations to determine if the bulletin has been previously received? That is called AMTEX, A-M-T-E-X. And what is the most common data rate used for HF packet communications? Down on high frequency, we have to slow down the rate, so we're down around 300 baud. All right, let's tighten up on the bandwidth and listen to MFSK. MFSK refers to sort of a supercharged RTTY signal, Millennium Frequency Shift Keying. And instead of simple RTTY with 2 tones, MFSK uses 16 tones, one at a time, spaced at 15.625 hertz apart, 15.625 baud, with a very narrow bandwidth of 316 hertz bandwidth. It's not quite as narrow as the 31 hertz phase shift keying. That's what we're listening to right here, phase shift keying. But do know that MFSK 16 signal is 316 hertz. Which of the following HF digital modes can be used to transfer binary files? That would be PACTOR. And the BADO code is the International Telegraph alphabet number 2, which uses 5 data bits. And our final question on radio waves and signals will be, which of these digital communication modes has the narrowest bandwidth? AMTOR, RTTY, 300 baud packet? Nope, it is this, phased shift keying. And that agrees with question E2E12, PSK31, standing for phase shift keying. All right, now we've covered operating procedures, of which on your examination you will have 5 questions. A question on satellites, one on television, one on contest and DX operating, one on operating VHF, UHF digital modes, and finally, the last question out of 5 on operating procedures that we've just covered, operating HF digital modes. Well, what do you say we now tune into the Earth and the ionosphere and look at radio wave propagation? Ready to listen to the sounds of the Earth? Isn't that the strangest thing you've ever heard? Yep, that's the sound of spherics, the natural sounds of a type of radio reception we're able to hear coming from the ionosphere, atmosphere, and the core of the Earth, spherics. Well, let's talk about radio waves, and we will have 3 questions on your upcoming extra class examination about radio wave propagation. 1 question on EME moon bounce, 1 on transequatorial, long path, and gray line propagation methods, and 1 on auroral propagation. So what do we say we tune in to the moon? Is that amazing?
That was 40 dB in it.
Wow, 40 dB? And it's still coming through. That is moon bounce at its best. CW signals.
How did you do that trip?
CW signals coming off of the moon. Listen to that. Wow, just amazing. Well, what is the maximum separation between two stations down here on Earth communicating via moon bounce? And normally moon bounce is almost always done with CW or possibly some of the digital modes, mainly CW. Well, the maximum separation could be any distance as long as both stations have a mutual lunar window. As long as we can both see the moon, we have a good shot of working moon bounce. And what characterizes libration fading of an Earth-Moon-Earth signal, and that is a fluttery, irregular fading. When scheduling Earth-Moon-Earth contacts, which of these conditions will generally result in the least path lost? And that is when the moon is at perigee. Now, perigee is the time when the moon is closest to the Earth. Think of perigee as pair for perfect conditions for EME to occur. What type of receiving system is desirable for Earth-Moon-Earth communications? Well, you need something in your equipment with very low noise figures. And what transmit and receive time sequencing is normally used on 144 megahertz when attempting an Earth-Moon-Earth contact? Well, on 144, we use 2-minute sequences where one station transmits for a full 2 minutes and then receives for the following 2 minutes. Now, what about transmit and receive time sequencing for the 432 megahertz band? Well, on 432, we use 2.5 minute sequences where one station transmits for a full 2.5 minutes and then receives for 2.5 minutes. So 2.5 minutes for the 432 contacts and 2 minutes for the 2-meter contacts. And what frequency range would you normally tune to find EMA stations in the 2-meter band? Way down there at the bottom of the band, 144 to 144.100. How about on 432? We would tune in for moonbound stations 432 to 432, 100. Incoming, incoming, the meteors are incoming. Wow, that was pretty good. A 7 coming in down here on 6-land territory in Southern California. Well, meteors. Meteor showers provide some exciting time for amateur radio operators. In January, we have the quads. In May, the Aquariids. In June, the Ariids. In August, the Perseids. And December, the Geminids. These are some of the biggest meteor showers where when you call CQ, there's no telling where you're going to be hearing beyond maybe 500 to 1,500 miles away. Let's try it here on 2 meters. Let's try a quick CQ and see what we come up with, okay?
WB6 Nancy, Ocean America, QRZ.
WB6NOA, Kilo Juliet 7 Fox, S2.
KJ7F, WB6NOA 5454, Delta Mike 13, over.
Roger, here, 5 and 9, Delta Mike, Delta November 13, over.
Okay, where are you located?
Boise, Idaho, Delta November 13.
Wow, you're pounding in, 5 and 9.
Wow, that was pretty good. That was out at about, I'd say 800 to 1,000 miles away on 144.200 on 2-meter single sideband. And I should have given him a report of S2, which is the way we normally report on meteor contacts. When a meteor strikes the Earth's atmosphere, a cylindrical region of free electrons is formed, and they want to know for the test, what layer does this take place in? Well, it occurs in the E layer. What range of frequencies is well suited for meteor scatter communications? Well, they give you some low band frequencies, 1.8 to 1.9 megs. They give you something on 20 meters. They give you 220 to 450, and while it's been done there, the best would be answer C, 28 to 148 megahertz, best for meteor scatter. What transmit and receive time sequencing is normally used on 144 megahertz when attempting a meteor scatter contact? And I might add, by prearrangement. And by prearrangement, you agree ahead of time the exact frequency. And you use 15-second sequences, where one station transmits for 15 seconds and then receives for the following 15 seconds. Meteor scatter, an exciting way of staying in touch for brief periods of time on the ham bands. Wow, this is pretty exciting on VHF, and that's called transequatorial propagation, question E3B01. Transequatorial propagation, sometimes abbreviated TE, is propagation between 2 points at approximately the same distance north and south of the magnetic equator, many times occurring on the lower VHF bands. Now, the approximate maximum range for signals using TE could be up to 5,000 miles, 2,500 miles north and 2,500 miles south of the equator. And the best time of day for transequatorial propagation, especially on the 6-meter band and maybe even 2 meters for brief periods, would be afternoon or early evening hour. You are going to have so much fun on the extra class portions of the band because you'll be there all by yourselves, not having to share it with anyone. And many times you can obtain some long-range radio transmission and reception with your directional beam antenna exactly 180 degrees out from where it should be pointed short path to that distant station. Now here I am one night beaming in a direction 180 degrees out, and listen to this contact coming through.
November Oscar Alpha, Victor Kilo 2 Alpha Golf Tango. Very fine business and a very, very good evening to you all there in the shack, especially your students. Nice to meet you all. And
this is Lord Howe Island.
Here at the moment, you're 56, 5 and 6 on Lord Howe. We are a fixed permanent station on the island, and in fact the only station working on the DX band south of Lord Howe Island. Lord Howe Island is really part of Australia, but as far as DXCT is concerned...
Now, this is with my antenna pointing almost due north, yet the station is more to my south. So we're approaching this station via what we call long path communications. Now, in which amateur bands can long path propagation provide signal enhancement? Well, that could be all the way to the bottom 160 meters up to 10 meters. What amateur band consistently yields long path enhancement using a modest antenna of relatively high gain? Well, the best band is, yep, you got it, the 20-meter band. And many times you will hear an echo on the received signal of a station, let's say in Europe, while directing your HF antenna toward the station. Well, the reason is you're actually picking up two signals at the same time, one from the direct path and one from long path. So those European stations many times will come in with a echo. And it'll take a few turns of the beam antenna to determine which way the signal is going to come in best. Sometimes long path, sometimes short path. Well, another exciting type of propagation is called gray line. It's a propagation that occurs when signals travel along the area of sunlight and darkness, called the terminator. Gray line propagation. And the time of day that gray line propagation is most prevalent is twilight, at sunrise and sunset. We'll be in sunrise, the other station will be in sunset. Or we'll be in sunset and stations to our west will be in sunrise. Now, what communications are possible during gray line propagation? Contact sometimes up to 8,000 to 10,000 miles away, sometimes occurring on 3 or 4 HF bands simultaneously. You're going to enjoy your extra class license because you'll be able to take part in all of this type of propagation, especially gray line. All right, I have a question for you. How many of you live in the northern portion of the United States? And how many have seen an aurora? All right, let's see your hands. Well, keep your hands on the wheel if you're driving. Okay, auroras. Well, auroras will have a tremendous effect on VHF and UHF communications. And the cause of auroras are the emission of charged particles from the sun. And during periods of major sunspots, auroral activity will normally be high for at least a year or two after the peak of the solar cycle. Now, what does aurora sound like? Oh, I'm glad you asked. Here we are listening to an aurora signal when I was up in Alaska on the 2-meter band, and this is CW. Well, it's the strangest CW that you've ever heard. No tone. Well, they ask on the examination, what effect does the auroral activity have upon radio communications? Well, for one thing, CW signals will have a fluttery tone. Certainly not clear. No FM. Sideband will be pretty strange. In fact, if you were to listen to a voice on single sideband that was totally obscured by an aurora, here is what a SSB 2-meter signal from Alaska sounds like via aurora. That's someone talking. Isn't that the strangest sound you ever heard? Well, on the worldwide bands during an aurora, especially up in the northern portion of the country, as well as Canada and Alaska, this is what you'll hear during the peak of an aurora on your popular 20-meter band. That's it. That's what you're going to hear on 20 meters. Nothing from one end of the band to the other, but static. And then all of a sudden, after the aurora passes overhead, guess what pops out at 20 meters? Now, do you hear that rapid flutter? That's aurora. 6/6/6 monoband Yagis. Yeah, that's quite a nice station in Barcelona. Now, where in the ionosphere does auroral activity occur? Well, it occurs, again, just like meteors, in the E region height. And what emission mode is best for auroral propagation? Well, CW is always the best. That'll get through the rapid fading and some of the very strange sounds of auroral communications. There are so many exciting types of emissions when you're out there with your new extra class license. Chances are you've maybe tried FM working ionospheric skip on 6 meters, as well as FM on the 10-meter band. That's right, FM at the top of the 10-meter band. A problem, though, is when FM, which is a relatively wide bandwidth signal, bounces off the ionosphere, many times it becomes distorted due to selective fading. Selective fading are phase differences between radio wave components of the same transmission as experienced at the receiving station. Now, listen to me here on the West Coast, hearing the station on FM 10 meters coming through. The signal strength is very strong, but the intelligibility will change as selective fading makes the signal go from clear to garbled.
I am located in Stoneham, Massachusetts. That's S-C-O-N-E.
There's the selective fading.
North of Boston. I'm using a 3-element 11-meter.
Now it comes up clear again.
Meters, about 20.
So all that grungy noise is called selective fading, and that occurs with wide bandwidth signals. Now, how far do radio signals go, especially those at VHF and UHF radio bands? Well, they go normally line of sight and 15% beyond that distance. So how much further does VHF, UHF radio path horizon distance exceed the geometric horizon? By approximately 15%. That is the refraction of VHF and UHF waves. Now, if you're going to put up that new extra class 3-element beam antenna with horizontally mounted elements, how does the main lobe takeoff angle vary with height above flat ground? Well, the lobe will decrease the higher up you put your beam. So to answer this question E3C08 correctly, the lobe decreases with increasing height. Now be careful, that's sort of a tricky answer. And what is the name of the high angle wave in HF propagation that travels for some distance within the F2 region? That's called the Pedersen ray. And what effect is usually responsible for propagating a VHF signal over 500 miles? Well, I'm happy to say I hold one of the records on that, and that effect is called tropospheric ducting.
This is King Henry 6 Hotel Mike Echo, located on the big island of Hawaii.
Now, this is picked up by good old Gordo here in Southern California, Hawaii.
Mauna Loa, which is a volcano.
2,500 miles.
Elevation, 8,200 foot.
Coming in crystal clear for 5 to 7 days at a time.
West.
On VHF and UHF, that's right. Can you imagine 2 meters and 432?
So how does that,
Now listen to this. You won't believe this.
still holding up to the Gordon?
Yeah, it sure is, Paul. Tell us what mode you're on and tell us what frequency, over.
We're on 432.0740 on FM. FM 432.074. Real nice signal out here. You got enough signal strength so it's 100% quieting at the present time.
Okay, Paul, how far apart do you think we are?
2,500 miles.
Wow, now that's pretty good for an FM contact, and this is thanks to tropospheric ducting. So if you live along the ocean, chances are you may be reaching out a lot further than what you thought on your VHF and UHF frequencies. Now, let's get back to high frequency. Question E3C11 for a 3-element beam antenna with horizontally mounted elements. How does the main lobe takeoff angle vary with the downward slope of the ground? Hopefully you live on a big cliff. Well, the takeoff angle will decrease. And remember, the lower the takeoff angle, the better. It will decrease as the slope gets steeper. In the northern hemisphere, in which direction should a directional antenna be pointed to take maximum advantage of auroral propagation? Well, remember we played you Aurora a few moments ago. We normally head our antennas north. As the frequency of a signal is increased, how does its ground wave propagation change? Normally, the higher we go in frequency, ground wave propagation will decrease. And what type of polarization does ground wave propagation have? Normally, we use vertical polarization for ground waves. But those of us on 2 meter and 432 single sideband, we actually operate horizontal. But to answer this question, E3C14 correctly, what type of polarization does ground wave propagation normally have? Normally it is vertical. And why does the radio path horizon distance exceed the geometric horizon? That is because radio waves may be bent, or refraction.
Roger. Thank you very much for the QSO 10-3.
73, thank you again.
Wow, when you get your extra license, 6 meters may sound many times like 20 meters. When you put up that big extra class antenna and start working some of the HF bands where you have new privileges for, don't forget all the excitement though up here on VHF and UH. Now, radio wave propagation will have 3 examination questions in 3 groups coming up on your test, your 50-question test. 1 question out of radio wave propagation will be Earth, moon-bound communications. 1 might be on trans-equatorial, long path, or gray line communications. Maybe you get something on meteor or auroral propagation, selective fading, and the radio path horizon. All right, now it's time to take a well-deserved break. We've just completed Subelement E3, radio wave propagation in preparation for your extra class license. We'll start up shortly with amateur radio practices. Take a break.
Please don't work the JH1 that's on the frequency. And it doesn't change, over.
You're going to have such a great time getting on high frequency, especially in those extra portions of the band. But before we get through that test, we need to take a look at amateur radio practices, of which on the examination for extra there will be 5 exam questions. Now, practices talks about test equipment such as spectrum analyzers that we use, frequency counters, receiver performance, noise suppression, component mounting techniques, circuit boards. It's going to be easy, so just sort of sit back and relax, and I'll try and delay before I give you the right answer and see if you can come up and beat me right here on this audio course with the correct answer. E4A01, how does a spectrum analyzer differ from a conventional oscilloscope? Well, a spectrum analyzer displays signals in the frequency domain. Oscilloscope displays them in a time domain. What parameters does the horizontal axis of a spectrum analyzer display? Well, horizontally it shows frequency. So we can take a look at a group of frequencies. Right now I'm working a radio with a spectrum analyzer band scope hooked up to it, and I can tune around and see where all the activity is just by looking on the scope. That's a form of spectrum analyzer. What parameter does the vertical axis of a spectrum analyzer display? Now this is the vertical. We know horizontal is frequency. The vertical is amplitude. And which test instrument is used to display spurious signals from a radio transmitter? Maybe you're working on one on the bench and you want to make sure that beside the fundamental frequency you don't have a whole bunch of spurs all over the place. Again, we would use that's right, spectrum analyzer. How about to display intermodulation distortion when testing your SSB transmitter? Again, the spectrum analyzer. Now, which of the following is not something that you could do with a spectrum analyzer? Well, one thing that you cannot determine with the spectrum analyzer is the speed at which a transceiver switches from transmit to receive when being used for packet radio. So if I'm testing my Pactor transmitter, I better take a look at it on an oscilloscope, not a spectrum analyzer. Now, there is an advantage of using the spectrum analyzer when observing the output from a VHF radio that I maybe have taken apart here on the test bench, because the spectrum analyzer displays all frequency components of the transmitted signal. All right, now let's shift gears and take a look at the logic probe. What advantage does a logic probe have over a voltmeter for monitoring the status of a logic circuit? Well, the logic probe is smaller and shows a simplified readout. Now that simplified readout is a high and low digital voltage state, which we can check with a logic probe. And what can a logic probe indicate about a digital logic circuit? The high and low states. And which of the following test instruments can be used to indicate pulse conditions in a digital logic circuit? Well, for pulse conditions, again, the logic probe. And which of the following procedures should you follow when connecting a spectrum analyzer to a transmitter output? Now, did you notice what happened here? 1 minute we're talking about logic probes, and then all of a sudden here comes the spectrum analyzer question out of place. Well, that's because as we made up the all-new extra class question pool, instead of having time and plenty of time to put all the questions together, at the last minute questions were added and subtracted to the pool. So sometimes, just like we had on beam antennas, we'll find a question that's a little out of place. Well, back to that last question dealing with the spectrum analyzer. Make sure when hooking it up to your equipment, you must attenuate or reduce the transmitter output going into the spectrum analyzer. Here at my test bench, where I'm transmitting from right now to you on this audio medium, I always use a inductive pickup. I never hook up a transmitter directly to the output antenna that would then go to my spectrum analyzer. That could very well damage the spectrum analyzer. All right, now let's tune in to this station that I know that you know real well.
At the tone, 18 hours, 33 minutes, Coordinated Universal Time.
WWV. We can use WWV as a frequency standard. That's a device used to produce a highly accurate reference frequency. And WWV is on your worldwide high-frequency radio 24 hours a day. And the way I test to make sure that my radio is absolutely on the nose is I go to WWV at either 10 megahertz with all zeros trailing after 10 or 15, and I usually tune it in the upper sideband mode. And if I go between upper and lower sideband, that wasn't right, was it? That points out that I am not zero beat on the channel if one is higher than the other. So what I'll do is I'll go into the radio, find the little tiny trimmer capacitor that is off the main crystal, and go ahead and calibrate it. Right now, it looks like I'm about 30 cycles off. Hear those two different tones? So use WWV as a great way to calibrate your high-frequency radio. What factors limit the accuracy, frequency response, and stability of a frequency counter? Well, every good ham should have a frequency counter. Well, what would limit the accuracy and response and stability would be the time-based accuracy, the speed of the logic, and the time-based stability. How can the accuracy of a frequency counter be improved? Buy a more expensive one. Well, we do that by increasing the accuracy of the time base. That will increase how much bucks you're going to spend for a frequency counter. All right, here come 6 questions that you can actually do in your head about the counter readout error of a frequency counter. First one says, if you had a frequency counter that is accurate to plus or minus 1 ppm part per million, and you're reading out 146,520,000 hertz, what is the actual frequency being measured could differ from the reading on your counter. 1 part per million. Okay, well, when we see ppm, we need to change hertz to megahertz, move the decimal point 6 places to the left. So now it's 146.52 megahertz, the national simplex frequency. 146.52 times plus or minus 1 part per million is 146.52 hertz of total potential error. Now, if you had 0.1 part per million specified accuracy of the counter, and you're on 146.520000 hertz, which would be 146.52, we'd multiply 0.1 times 146.52, and that comes out 14.652 as the total potential error. Now let's do a counter with 10 parts per million potential accuracy. Ooh, 10 parts, that's not very good, plus or minus 10 parts. 10 times 146.52 comes out 1,465.2 hertz of potential error. Then they asked remaining questions on the 432, 100, 000 hertz band. First thing is let's change 432 over to megahertz, 432.1 megahertz. And the frequency counter is, oh, this one's not bad, plus or minus 1 part per million. 1 times 432.1 comes out 432.1 hertz potential error. 0.1 parts per million times 432 would be 43.21 hertz error. And that counter of 10 parts per million times 432.100 would come out 4,321 hertz. So to solve one of these 6 problems, simply multiply parts per million times the frequency that you change from hertz to megahertz by moving the decimal point 6 places to the left, and that comes out in hertz as the potential error. Next question, E4B10. If a 100 hertz signal is fed into the horizontal input of an oscilloscope and a 150 hertz signal is fed into the vertical input, what type of figure will be displayed on the screen? Well, you'll have a looping pattern with 3 loops horizontally and 2 loops vertically. This is a 3 slant bar 2 relationship, so you will see a looping pattern, 3 loops across for 150 hertz and 2 loops vertically for 100 hertz. What is a dip meter? Oh, that's a good thing to have around the ham shack. That's a device consisting of a variable frequency LC, L for inductance, C for capacitance oscillator, and an indicator showing the meter feedback current. That's a dip meter. And MFJ makes one of the most popular SWR analyzers that, when hooked up to different circuits or antennas, is a great dip meter. What does a dip meter do? It gives an indication of the resonant frequency of a nearby circuit. How does a dip meter function? Well, power is coupled from an oscillator, and that causes a decrease in metered current. So we see a dip because it's actually coupled from the oscillator into the resonant device that you're testing. What 2 ways could a dip meter be used in an amateur station? Well, you could measure the resonant frequency of antenna traps, and you could also measure a tuned circuit resonant frequency. Now, for best accuracy, how tightly or loosely should a dip meter be coupled with the LC circuit being checked? Maybe you've got a coil on the bench. Well, you want it as loosely coupled as possible, in that you might get a false reading if you put it directly onto the coil or you get it too close. All right, now we're back to the oscilloscope. What factors limit the accuracy, frequency response, and stability of an oscilloscope? Well, that would be the accuracy and linearity of the time base and the linearity and bandwidth of the deflection amplifiers. What happens in a dip meter? See, don't ask me why that oscilloscope question is right there in the middle of the dip meters. Anyway, what happens to a dip meter when it's too tightly coupled with a tuned circuit? Well, we've talked about that. A less accurate reading will result. Now let's go to a needle type of meter called a d'Arsenval meter. What factors limit the accuracy, frequency, response, and stability of a d'Arsenval type needle reading meter? Well, that would be calibration, mechanical tolerance, and the coil impedance. How can the frequency response of an oscilloscope be improved? Here we go. We're jumping back and forth. Not me. This is the question pool. All right. Question E4B19 on the oscilloscope. How can we improve the frequency response? Well, we could increase the horizontal sweep rate and the vertical amplifier frequency response. All right, I've just completed work on my new VHF multi-mode radio, and I'm going to be doing some testing of the phase noise in the local oscillator section of my receiver. And I'm going to try 2 different transistors. Now, you tell me which you like better. Do you want this amount of noise for a given signal or this amount? Again, this or this? This or this? Not a lot of change, but enough that if a real weak signal were coming in, it could be lost in the noise. What is the effect of excessive phase noise in the local oscillator section of a receiver? It would allow strong signals on nearby frequencies to interfere with reception of weak signals. So that's why we don't have a lot of phase noise in a local oscillator of a good receiver, because someone nearby would begin to swamp our receiver and cover up the weak signal I'm trying to tune in. Now, that's probably happened to you on your little FM handheld, your little walkie-talkie. They call the term for the reduction of receiver sensitivity caused by a strong signal near the received frequency desensitization, or sometimes called desense. And which of the following can cause receiver desense? Strong adjacent channel signals. Which of the following is one way receiver desensitization can be reduced? Well, improve the shielding between the receiver and the transmitter causing the problem. Now, take a listen to the 24-hour weather service that I'm listening to when someone nearby is with their little 2-meter handy transmit. Hear the noise? Clear. Noise. Clear. Noise. Clear. Noise. Noise. Yeah, that is called desensitization. And the cure is to have them either turn down the power or for me to get further away. All right, it's now time to take a break before we talk a little bit about capture effect. So capture a few Z's, go out and wash the car, mow the lawn, pet the cats and dogs, groom the horses, and I'll see you back here in just a few. Take a break. If you're listening to us on audio cassette, it's time to turn the cassette over.